In math, we know that there are several basic properties that form the fundamentals of algebra. So for example, we know that a plus b always equals b plus a, or that a plus b plus c in parentheses equals a plus b in parentheses plus c, or even that a times b plus c equals a times b plus a times c. And it turns out that in the world of limits, there are also several basic fundamental properties. So the first property says the limit as x approaches a for c times f of x equals c times the limit as x approaches a for f of x, where c is just some constant or some real number, okay? And let's illustrate this property by giving some examples. So let's say that the limit as x approaches 4x squared. So before I use this property, let's just try and solve this limit by itself by using direct substitution. So direct substitution says that we can just input the value that x approaches into the general function, which is 4x squared, right? So what we do is we just input 2 into the function. So we get 4 times 2 squared, which is 4 times 4, which is 16. And now let's use this property here. So if we follow the same structure, we can see that 4 would be our c, and x squared would be our f of x, right? Because 4 is just a constant, a real number, doesn't depend on x. And according to the property, they're saying that if we move this c outside of the expression, we get the same result. So let's see if that happens. So if I move 4 outside, I get 4 times the limit as x approaches 2 for x squared. And this, to calculate this, we just input 2 into x squared. So that would be 2 squared. So we get 4 times 4, which is 16. So it turns out that they do have the same result. So the next property says that the limit as x approaches a for f of x plus g of x equals two separate limits, the limit as x approaches a for f of x plus the limit as x approaches a for g of x. So again, I'm going to try and help illustrate this property by using an example. So let's say the limit as x approaches 4 for x squared plus x cubed. And without using the property, to calculate this, we just input 4 into this general function here, which is x squared plus x cubed. So that would just be 4 squared plus 4 cubed, which would be 16 plus 64, which would be 80. And now let's use this property. So according to the property, this would be f of x, and this would be g of x, right? So x squared is the f of x, then plus g of x, so x cubed. So that means that we would separate this into two separate limits, which could be rewritten as the limit as x approaches 4 for f of x plus the limit as x approaches 4 for g of x. And to calculate this, we just use direct substitution. We input 4 into the function, so we get 4 squared, and then we get here, we get 4 cubed, right? So that would be 16 plus 64, which would be 80 once again. So this next property is actually very similar. You're just replacing the addition signs with minus signs. And to continue illustrating this, or showing how this property works, let's say I have the limit as x approaches 3 for 7x squared minus 7. And once again, if I don't use this property, what would I do? Well, I would just assume this is my overall function, and I plug in 3 into the function. So I get 7 times 3 squared minus 7, which is 7 times 9 minus 7, which is 63 minus 7, which is 56. Now, using the property, I will define 7x squared as f of x and 7 as g of x, because constants can be functions, right? 7 can be a function on the graph. It would just be a horizontal line. So using the property, I could rewrite the expression as the limit as x approaches 3 for f of x minus the limit as x approaches 3 for g of x. And to calculate the first one, we just input the value that x approaches into the function once again. And we get 7 times 3 squared minus, and for this one, if you don't immediately know, well, that's because you can't exactly use direct substitution. But if you do visualize it on a graph, 7 is just a straight horizontal line, right? So that means that as x approaches 3, it doesn't really matter where x even approaches, because y is always going to be 7. So y always approaches 7. So now we get 7 times 9 minus 7, which is 63 minus 7, which is again 56. And I'm going to use another property here. I'm going to say that you can rewrite this expression right here as the limit as x approaches 3 for 7 times x squared minus 1. Right? So I'm just factoring out a 7. And the reason I did this is because I noticed that you can just say 7 is a constant and x squared minus 1 is a function. And that's the first property, right? Whenever you have a constant, you can just move it out here. So I could just rewrite this as 7 times the limit as x approaches 3 for x squared minus 1. So using direct substitution again, plugging in 3 into this function will give me 3 squared minus 1, which would be 9 minus 1, or 7 times 9 minus 1, and 7 times 8, and 56 again. So you can see that these three values are all the same. So this next property says that the limit as x approaches a for f of x times g of x equals the limit as x approaches a for f of x times the limit as x approaches a for g of x. So you can see a similar pattern. These are two separate limits again. But I'm also going to try something different to help visualize these functions. So this time, well, not functions, these properties of limits. So this time let's say that a equals 1, f of 1 equals 3, and g of 1 equals 5. So these are just functions, the f of x and g of x. I'm inputting 1, right? I'm getting outputs. And now let's try and rewrite the expression. So this would just be the limit as x approaches 1 and for f of x times g of x. And to solve this expression, not using the property, just to solve it how you would use it or do it normally, right? What you would do is you would just input the value that x approaches into the overall function, right? Which is just direct substitution. So let's do that. So we would get, not the limit, we would just get f of 1 times g of 1, right? And we know that f of 1 is 3 and g of 1 is 5. So we would get 15. So now let's try this this property. So let's rewrite this expression, right, using the property. So according to the property, we can rewrite this as the limit as x approaches 1 for f of x times the limit as x approaches 1 for g of x. So let's see if it works. This limit right here, this first limit, all we're doing is we're just plugging in 1 into the function. So that would just be f of 1. This one right here is g of 1, right? F of 1 times g of 1. F of 1 is 3. G of 1 is 5. So we get 15 again. So you can see this property checks out here. So this next property is also similar. It's the limit as x approaches a for f of x over g of x equals the limit as x approaches a for f of x over the limit as x approaches a for g of x. So now let's just say that a equals 1 again, and f of 1 equals 6, and g of 1 equals 3. And if I wanted to rewrite this, this would just be the limit as x approaches 1 for f of x over g of x. And to solve this limit, not using the property again, I would just plug in 1 into my overall function, which would give me f of 1 over g of 1, which is 6 over 3, which is 2. Now, using the property, we're separating this into two limits. So we would rewrite this right here as the limit as x approaches 1 for f of x over the limit as x approaches 1 for g of x. And what will that give us? Well, what was the top limit? The top limit is just plugging in 1 into the function, right? So that will just be f of 1. The bottom limit is plugging in 1 into this function, so that will just be g of 1. And we know that f of 1 is 6, g of 1 is 3. So we get the same value again, which satisfies this property. And I can do another way to rewrite this here. I can rewrite this expression right here again as the limit as x approaches 1 for f of x times 1 over g of x, right? Right, these are the same, right? And this, you can use that last previous property where this is one function and this is another function. So these are two functions here. If you remember the previous property, if you have a function times a function, you can just separate them into two different limits. So this is actually just the limit as x approaches 1 for f of x times the limit as x approaches 1 for 1 over g of x. And the first limit, you plug in f of 1, or you plug in 1 to get f of 1. And for the second limit, you plug in 1 into this overall function here to get 1 over g of 1. F of 1 is 6, and g of 1 is 3. So you get 6 times 1/3, which is 6/3, which is, again, 2. So this next property says the limit as x approaches a for f of x to the nth power. So it's raised to some power, okay, some number, equals the limit as x approaches a for f of x and that entire thing, that entire value raised to the nth power. So now I can try to derive this. And to do so, I'm going to say I have the limit as x approaches a for f of x squared, okay? So this this function right here is squared. So not the entire limit. This right here, okay? And I want to rewrite this. So first of all, here is what I would do. I could say the limit as, this is the limit as x approaches a for quite just simply f of x times f of x, right? That's just basic algebra. And if you remember that property that I mentioned a few properties ago, it was if you have a function times a function, then what can you do? You can separate this into two separate limits, right? So this will just be the limit as x approaches a for f of x times the limit as x approaches a for f of x. And, well, these are the same thing. So if you have something times the same thing, something times itself, what can we rewrite that as? Well, we all know that x times x, or something times something, is just something squared. So this is just the limit as x approaches a for f of x squared. And notice how if you say this is n on the inside, you're moving it out to the outside, and in this case, that is what we did. So this next one is the limit as x approaches a for c equals c. So c is just some constant. And if you wanted to visualize this on a graph, c would just be, so f of x would just equal c, right? C would be any real number. And if you just have a real number, it would just be a horizontal line, right? Let's say this is c. Well, then the graph will just be a horizontal line. Or if it was here or here, it doesn't matter where you put it. It's always a horizontal line. And assuming here is c, okay. What I'm saying is if x approaches a for c, it equals c. So it doesn't even matter what value x approaches. A could be here or here or here. It doesn't really matter. Whatever x approaches, y will always approach c. And that's because it's just a horizontal line. Y doesn't move anywhere else. So it's always going to be c. So the limit as, let's say, x approaches 1 for c, right? What would equal c, right? The limit as x approaches negative 1 for c. It equals c. So this was negative 1 and this was 1. You can see that it's c once again. So this next property is the limit as x approaches a for x equals a. So if you wanted to graph this as well, then we would just have a straight diagonal line, right? Because x, f of x equals x, has a slope of 1. And I'm saying that whatever value that x approaches, y will approach that same value, right? And how can we visualize this? Well, if a is here, then that means y would be here. And y would also be a because the slope is 1. Whenever the slope is 1, however much you go to the right, you have to go that same amount to up, right? Or however much you go to the left, you have to go that same amount down, right? So that is why for a function x, if x approaches a, y will always approach a. If you have the limit as x approaches 10, y will approach 10. And if you use direct substitution, it also checks out. You plug in 10 into the function, and you get 10, right? The limit as x approaches 0, oh, it's 0, right? So just like the fundamental properties in algebra, the key is not to memorize these properties, but to intuitively understand why these statements are true, right? For example, for some of them, I used direct substitution and I used a property and I compared results. Or maybe I derived new properties using previously established ones. So you'll find that using these properties, you will be able to calculate limits much faster in many, many cases.